Hello, I'm Benjamin Meyer. I'm a junior mathematics major at Morehead State University in Kentucky.
Hello, my name is Ismael Abdullah, and I am also a mathematics major at Morehead State University.
We chose problem C, people ruin everything.
We chose to solve this problem using a system of ordinary differential equations based on the Ludka-Volterra model.
We hope you enjoy our presentation. For our problem, we were asked to model the reduction of anti-predatory responses of a prey species by interaction with a human population and its effect on the prey-predator system over time. Our model is a system of three nonlinear first-order ordinary differential equations. It is used to simulate the reduction of anti-predatory responses in the prey species. We based our model off of the predatory or prey model known as the Lotka-Volterra equations, where Y is the predator population and Z is the prey population. The time derivatives of Y and Z are based on the current populations of the prey and predator. Where A0 is the natural rate of decline of the predator species, A1 is the birth rate of the predator species as a result of successful predation, A2 is the birth rate of the prey species, and A3 is the successful rate of the predator attacks. In order to introduce a human population quickly, we used a simple logistic equation with a set carrying capacity. We used 2.3 as the average human fertility rate. Gamma is a special value we assigned to simulate the reduction of anti-predatory response in the prey species. It was assigned such that successful hunts occur twice as often at the population density of New York, which is roughly 11,500 people per square kilometer. Gamma is also time dependent. This comes from the t over 1 plus t factor in the gamma term. Putting all this together, gamma increases the rate of successful predation, raising the predator population but decreasing the prey population. We also added a term A, the rate at which the mere presence of humans kills off both species. This is signified by an additional term at the end of each species differential equation respectively. The value 0.025 was chosen for A3. This is based on real-life observations. What happens when a group of people enter a new area? Here's a stable outcome where humans live in harmony with two species. The population density is 1,000 people per square kilometer. On the right is the same system but with no gamma term. The peaks of the prey and predator populations are slightly lower in the system with the gamma term. The loss of anti-predatory responses acts to reduce both populations. Here an example of a degenerate solution where too many humans are introduced and it causes the extinction of both species. What happens when humans move out of a system? When humans leave a system, our model returns to a standard predator-prey system. Note that the peaks reached by the prey and predator species are higher and the periods are shorter, in this case by a ratio of roughly 4:3. Exploring other scenarios. Here we have two predator-prey species, one predator species, and humans, and a stronger gamma. We'll explore both. Interestingly, humans act as a regulator for the three species. Without the presence of humans, one of the prey species goes extinct. A new equilibrium is reached by the remaining species. For a strong gamma term scenario, a strong gamma term reduces the peaks and increases the periods of both species. And finally, an extremely high gamma term causes a feeding frenzy extinction.
Hello everybody. Let's go ahead and take a closer look at our equations. If we go over here to Mathematica, we can adjust some of the parameters that make our equation work. For example, if we were to increase alpha, which is the rate at which human beings cause a decline in the other two species population, and we were to plot that compared to our original graph, it indeed causes a degenerate solution. Just that small increase in the rate at which we kill the other species. And if we were to adjust it down by that same amount, and we were to plot that, It leads to a sustainable solution in which the population of both the predator and prey species are allowed to increase. So let's have a look at the three-body problem and see what happens there. If human beings decrease the amount at which they cause a decline in the other two species, or the other three species population, and plot that, it interestingly enough causes a solution where one of the species dies out and the other two species fall into a new equilibrium. And if we were to increase the amount at which we reduce the other three species population, and plot that, it leads to a degenerate solution where all three species go extinct. Alright guys, hello once again. So we may be interested in looking at the slope field for our system of ordinary differential equations. In this particular instance, the carrying capacity for the human population has been set to 10,000. Likewise, the other coefficients are the same as in the previous section. We go over here to wind plot. We can see our slope field a little bit more accurately. These two solutions over here in yellow and green respectively lie on the YZ axis, meaning that they represent solutions where human beings are not present. However, this solution in blue represents one where human beings are present at time 0. And of course, we can play around with these initial conditions as well. If we were to set the human population at 100 at time 0, and the prey population to 150, we get this particular solution over here. It is important to note that the solutions that lie on the YZ axis follow the same type of curve that you'd expect from a standard Lotka-Volterra system. However, not all solutions are cyclic. As you've seen in the previous section, there are degenerate solutions that represent cases where the human population causes the other two species to go extinct. So we can look at some of those examples as well. The carrying capacity for humans, in this instance, has been set to 30,000. That represents the highest human population density of any city in the entire world, and it is located in Dhaka, Bangladesh. As you can see here, the introduction of humans causes the extinction of the other two species. And this can be seen in the direction of the arrows on the slope field as you go further and further along the positive x-axis, which represents the human population. So to answer the question of whether human beings leaving the system can restore the system to the natural state, the answer is it depends. If the other two species, or in a multiple species system, if a species has gone extinct, they obviously cannot be brought back.
Hello once again. So in conclusion, what we have found in our model is that the suppression of anti-predatorial behavior in prey species negatively affects both the prey species and the predatory species as well.
Although the effect in our model is small, if the effect is significantly larger or the human population too large, it can cause the extinction of both species.
We hope you learned something and enjoyed our presentation.